electronegativity is a key property of atoms of elements that can crop up in any part of the A-level specification or the A-level course. But in today's video, I'm going to be primarily explaining what electronegativity is and how we can use electronegativity of different atoms to predict the type of structure and bonding that occurs within different substances. I'm going to focus on covalently bonded atoms to start with. Just a very quick recap then, a covalent bond is a shared pair of electrons. Now obviously there is a little bit more to that definition. Now we're looking at A-level chemistry, and it's actually the electrostatic attraction between the nuclei of the atoms that are sharing the electrons and the shared pair of electrons, but I'll elaborate on that a little bit later on. Now when we have atoms of the same element that are bonded together covalently, they actually share the electrons in the bond evenly. So they're shared evenly. Example we're going to look at first of all is hydrogen. So here's the dot and cross diagram of a hydrogen molecule. Got the shared pair of electrons in the overlap to represent the covalent bond. And here's a displayed formula of a hydrogen molecule. Now obviously we don't usually draw in the electrons in displayed formula. However, in this case I'm just going to add them in just because I want to show that if the atoms are the same element, in this case we've got two hydrogen atoms bonded together, the electrons that are in the covalent bond will be shared evenly, which means they will lie directly in the middle of the two nuclei of the two atoms that are bonded together. So they will lie directly in the middle or directly in the center of the two atoms. However, this will change when the atoms bonded together are different elements. The example we'll look at then is hydrogen chloride. So here's the dot and cross diagram of hydrogen chloride. Here is the displayed formula. Now what actually happens in this case is that the shared pair of electrons in this covalent bond actually lie more towards the chlorine atom. And the principle of electronegativity explains why that's the case. Now there are two main reasons why the sharing of electrons in a covalent bond will be uneven. Reason number one is the nuclear charge, so the number of protons in the nucleus. Obviously it's going to be different. If the atoms are different elements, then the nuclear charge or the number of protons is going to be different. They also may be different sizes. As a result, the shared pair of electrons will experience different strengths of attraction from the two nuclei of the bonded atoms. So if I go back to this hydrogen chloride example, and I said the electrons lie more towards the chlorine atom, this means that the attraction between the electrons in the bond and the chlorine or the nucleus of the chlorine atom is stronger than the attraction between the shared pair of electrons and the nucleus of the hydrogen atom, hence why they are more strongly attracted to the chlorine, so they will lie closer to the chlorine atom. This attraction between the nucleus and the shared pair of electrons is referred to as electronegativity. So the strength of this attraction between the shared pair of electrons and the nucleus is referred to as electronegativity. Now obviously different atoms of different elements have different electronegativities, and it's because of the two reasons that I mentioned earlier, nuclear charge and the size of the atom. Now it's actually measured, so electronegativity of atoms of different elements is measured and compared using something called the Pauling scale. So here we can see the Pauling scale for a number of different atoms of elements from the periodic table. So the numbers in the box represent the Pauling value, and the higher the value, the more electronegative the element. As we can see, that fluorine, actually has the highest value, making fluorine out of the elements on here, well in fact fluorine is the most electronegative atom on the periodic table. What does that mean? That means that fluorine, or fluorine's ability to attract the shared pair of electrons in the covalent bond, is stronger than any other atom of any other element. we can see that from the examples then that the group 1 metals, so lithium, sodium and potassium, they have quite low values, which means they are not very good at attracting electrons in a covalent bond towards themselves. So the more electronegative, the stronger the attraction between the nucleus and the pair of electrons in the bond. Now you'll notice then that the noble gases are not included because obviously noble gases don't tend to form compounds because they have their full outer shell. Now we can see different trends within this part of the periodic table of the electronegativity. And we can see that as we go down a group, we can see that, so from lithium to sodium, potassium, obviously hydrogen not included because technically we don't include it in group 1. Lithium, sodium, potassium, we can see that the electronegativity decreases. So they get, or the strength of attraction between the electrons and the nucleus gets less, okay, or gets weaker. Reasons for this then, so the shielding increases, so the number of inner shells is increasing, because remember, the electrons in the covalent bond are the outer shell electrons. So we're focusing on the outer shell electrons. And obviously as we go down the group, atoms get bigger, shielding increases. So those outer shell electrons are being shielded by more inner shells, which is going to make that attraction between the nucleus and the electrons weaker. Weaker attraction between the nucleus and the shared pair of electrons. As we go across a period, we can see that actually the electronegativity increases. So as we go across period 2 from lithium to fluorine, we can see that the value, the Pauling value, is increasing. Reasons for this then are the nuclear charge is increasing, so the number of protons is obviously increasing as we go across, and the atomic radius is actually decreasing, so the atoms are getting slightly smaller as we go across group to group. Even though they're in the same period, even though they have the same number of shells, the atomic radius is actually decreasing slightly. So that's why as we go across a period, the electronegativity increases, which means there's going to be a stronger attraction between the nucleus and the shared pair of electrons. Now we can use electronegativity to predict whether something is going to be ionic or covalently bonded. And we can use these principles here. So electronegativity values can be used to predict the type of bonding in a compound. If the difference in electronegativities is large, then the bonding is likely to be ionic. So the atoms are less likely to share because there's such a big difference in electronegativity. The atom that's more electronegative will take the outer shell electrons of the other atom. So we know then that in ionic bonding, the ions are formed by the transfer of electrons. The more electronegative atom is likely to take the outer electrons from the other atom, resulting in electron transfer occurring, which obviously is ionic bonding. Common example is sodium fluoride. So obviously when sodium atom reacts with a fluorine atom, they don't share electrons because the difference in electronegativity is so big. Fluorine is much better at attracting electrons than sodium. So the fluorine will actually take the outer shell electron of the sodium atom. So we've got this transfer of electrons. This is obviously going to form ions, a sodium ion and a fluoride ion. So obviously now we've got ionic bonding occurring. So if the difference in electronegativities is large, then the bonding is likely to be ionic. If the difference in electronegativity then is small or is 0, so you've got the same atoms bonded together, then the bonding is likely to be covalent because they're obviously both the two atoms are both fighting for the electrons, but if they're quite similar, neither one of those atoms is going to win out. So rather than taking electrons or transferring electrons, they will share the electrons. So the atoms are more likely to share the electrons as neither one is electronegative enough to take the electrons. So obviously that will result in a covalent bond. So for example, hydrogen bromide, the electronegativity values of hydrogen bromide are quite similar. So they will actually share the electrons rather than transferring them. And this table sort of gives you a rough idea, or you can use this to predict whether you think a substance is going to be ionic or covalent. So obviously, if there's no difference in electronegativity, then the bonding will be covalent. They will evenly share the electrons, and it will be a purely covalent bond. If the electronegativity difference between the two atoms is between 0 and 1.8, then we have something called a polar covalent bond. Now, I'm going to address polarity in my next video, so please do check that out. And then if the difference in electronegativity is greater than 1.8, then we predict that the bonding in that compound is likely to be ionic.